diagram shows apparatus that can be used to investigate the photoelectric effect. Okay. Light is shone onto a metal plate. For a particular metal, there will only be a current for frequencies of light greater than 8.17 times 10 to the 14 Hertz. Explain how this theory supports the particle theory of light. This observation supports the particle theory of light rather than the wave theory. So particle theory says that that light is quantized into packets of electromagnetic radiation called a photon. The photon carries energy. The photon carries energy which depends on its frequency. E is equal to hf. The photon carries energy which depends on its frequency. E is equal to hf. But the point is that this energy is in a packet. But this energy is in a packet. All of that energy, you can't split it up into different parts. It's only in one part. The energy is in a packet. The energy cannot be divided up, because it's a packet, it's quantized. So all this energy is given to one photon. Okay? So all the energy is given to one photon. Now we think of the electron, not one photon, one electron, sorry. One electron. The energy cannot be divided up, so all this energy is given to one electron. So we think of the electron as being at the bottom of what I call a potential well. A potential well. Like a well where you get your drinking water. Okay? So a potential well. There's a certain amount of energy needed to lift that electron out. To lift that electron out, there's an energy called the work function. The work function is the energy needed to remove the electron from the surface of the metal, and that is fixed for the metal. The energy can't be divided up, so its energy is given to one electron. The electron needs an energy called the work function to be released from the surface of the metal. So if work function, we'll call it phi, if the HF is less than phi, no electron is released. Okay. If HF is greater than phi, the electron is released and the leftover energy is given as the kinetic energy of the electron. Now that explains the particle theory. but we're asked to explain why wave theory this doesn't work. So now, if light is a wave, if light is considered to be a wave, then it's different, isn't it? We would have a wave is a continuous flow of energy. Okay, then energy flows continuously, not discrete, not up here like it was in packets, discrete packets of energy. This is, if energy is a wave, then the energy would flow continuously, independent of the frequency, no matter what frequency, no matter what the frequency. If light is considered a wave, then energy flows continually, no matter what the frequency. This means energy would eventually build up in the electron until there is enough to overcome the work function. It does not matter what the frequency is. Even a low frequency wave would eventually build up enough energy for this to happen, even for a low frequency. If the applied potential difference is reversed and increased, the current will decrease, and at a certain value of the potential difference, the current will be zero. So we call that the stopping potential, don't we? Calculate this potential difference when the frequency of the incident light is 9.62 times 10 to the 14 hertz. So now, this is the threshold. We call this one the threshold frequency, don't we? So when the electrons are released, they're carrying kinetic energy. At the stopping potential, that means that that electron has just been stopped. So at the stopping potential, work done by the potential, work done by, at the stopping potential, work done by V is equal to the loss of the kinetic energy of the electrons. So the Ke of the electrons, Ke max of the electrons, we can get from HF minus phi, what we've explained down here, okay? It's the energy coming in minus the work function gives us the kinetic energy. So we can actually get, and the work done by the voltage is QV is equal to Ke. So actually we can get QV is equal to HF minus phi. So V is equal to HF minus phi over Q. So we got 6.63 times 10 to the minus 34 minus, times, well, actually let me just make this even more simple here. It's going to be HF minus HF0, isn't it? Okay, HF minus HF0 over Q. So it's actually 9.62 times 10 to the 14 minus 8.17 times 10 to the 14 over the charge on one electron, which is 1.6 times 10 to the minus 19. Let's put in my calculator. 6.63 times 10 to the minus 34 times 9.62 minus 8.17 14 over 1.6 times 10 to the minus 19 gives me a stopping potential of 0.6